Hi everyone, my name is Dr. G. Naga Malleswari, Assistant Professor, Department of Mathematics from VNR JYOTHI Institute of Engineering and Technology, Hyderabad. In today's lecture, we discuss bilinear transformation in conformal mapping. Here, we have to discuss bilinear transformation definition, fixed points, cross ratio and its properties, determination of bilinear transformation, mapping 3 given points to 3 assigned points. Let us begin with the definition of bilinear transformation. Bilinear transformation. Another name of bilinear transformation is Mobius transformation. The transformation W is equal to AZ plus B by CZ plus D, where A, B, C, D are complex constants and AD minus BC is not equal to 0 is known as bilinear transformation or Mobius transformation. So first point here we have to discuss is a bilinear transformation is conformal. Bilinear transformation is conformal means it preserves. So first point here we have to discuss is a bilinear transformation is conformal. A conformal map is one that preserves angle between the curves. Under the transformation, angle between the curves at any point remains unchanged. Next, second point is there is one-to-one correspondence between all points in two planes. So one-to-one correspondence means here take two planes. One is Z plane and another one is W plane, x-axis, y-axis, here it is U, V. One-to-one correspondence. So that means each point in the Z plane, this is domain, has unique image in W plane, codomain, and vice versa. So that there exists one-to-one correspondence between all points in the two planes. Invariant or fixed points of bilinear transformation W is equal to AZ plus B by CZ plus D. Fixed point. So fixed point means a fixed point is a point that maps itself under the transformation. So if we substitute W is equal to Z then the equation becomes Z is equal to AZ plus B by CZ plus D. Solving this, we get the fixed points. So first point that we have to discuss under fixed points is, if suppose it is the identity function W is equal to Z. Here every point is a fixed point. Every point is a fixed point. Next, take another transformation, that is W is equal to 1 by Z. W is equal to 1 by Z has two fixed points. A bilinear transformation whose fixed points are alpha and beta, then W is equal to gamma Z minus alpha beta by Z minus alpha plus beta plus gamma. So these 3 points that we have to remember, and these 3 points are important points under fixed points. Next point here is Every bilinear transformation maps the totality of circles and straight lines in the z-plane onto the totality of circles and straight lines in the w-plane. So this is another important point in Mobius transformation. A circle in z-plane or a straight line in a circle in z-plane becomes a straight line in the w-plane, or the straight line in w-plane becomes a circle in the z-plane. So that every bilinear transformation maps totality of circles and straight lines in the z-plane onto the totality of circles and straight lines in the w-plane. Next point is a bilinear transformation preserves the cross ratio property of 4 points. Take 4 points. So the points that we are taking here are Z1, Z2, Z3 and Z4. Cross ratio property of 4 points, Z minus, here we are taking the points of Z1, Z2, Z3 and Z4. So cross ratio of 4 points is Z1 minus Z2, Z1 minus Z3, Z2 minus Z4 by Z1 minus Z4 into Z2 minus Z3. So this is the formula for cross ratio property of 4 points. Next, another property is 3 given distinct points. Distinct points that we are taking here are Z1, Z2 and Z3 can always be mapped onto 3 crossed distinct points W1, W2 and W3. Z1 mapped to W1, Z2 mapped to W2, Z3 mapped to W3 by one and only one linear fractional transformation W is equal to f of z. So this mapping, which is given by the equation W minus W1 into W2 minus W3 by W minus W3 into W2 minus W1 is equal to Z minus Z1, Z2 minus Z3 by Z minus Z3 into Z2 minus Z1. So this is the formula for 3 given distinct points Z1, Z2 and Z3, which are mapped onto 3 crossed distinct points W1, W2 and W3. And one important point that we have to remember here is if one of these points is infinity, so one of these points means either Z1 is infinity, Z2 is infinity or Z3 or W1, W2, W3. One of these points is infinity, then the quotient of 2 differences containing this point must be replaced by 1. See the example problem for better understanding of bilinear transformation. Find the bilinear transformation which maps the points -1, 0, 1 into the point 0, I, 3i respectively. We have to find out the bilinear transformation. Points are given -1, 0, 1 into the points 0, I, 3i respectively. So first take the points given Z1 is equal to -1, Z2 equal to 0, Z3 is 1 and W1 is equal to 0, W2 is equal to I and W3 is equal to 3I. The required bilinear transformation. The required bilinear transformation. Required bilinear transformation is formula W minus W1 W2 minus W3 by W minus W3 into W2 minus W1 is equal to Z minus Z1 into Z2 minus Z3 by Z minus Z3 into Z2 minus Z1. Substitute the points. In place of Z1 we have to take minus 1, Z2 is 0, Z3 is 1. And W1 is 0, W2 I, W3 is 3I. Substitute the values here. W minus W1 is 0 into W2 I minus W3 is 3I by W minus 3I into W2 I minus W1 0, which is equal to Z minus, what is Z1? Z1 is minus 1. So minus of minus 1 we get plus 1 here. Z2 0 minus Z3 is 1 by Z minus Z3 is 1, Z2 0 minus of minus 1, because Z1 is minus 1, we get plus 1. W into I minus 3I by W minus 3I into I is equal to Z plus 1 minus 1 by Z minus 1 into 1. Next, W into I minus 3I is minus 2I by W minus 3I into I equal to minus of Z plus 1 by Z minus 1. Here in denominator I is there, numerator I is there. Cancel this. We get minus 2W by W minus 3I is equal to minus of Z plus 1 by Z minus 1. Next, cross multiply this one. Here minus is there, minus, cancel these two. Then we get 2W into Z minus 1 is equal to Z plus 1 into W minus 3I. That implies 2WZ minus 2W is equal to ZW minus 3IZ plus W minus 3I, which implies 2WZ minus 2W minus ZW minus W, which is equal to minus 3IZ minus 3I. Two WZ, and here minus 2W is there, and here minus W is there. We get minus 3W minus ZW is equal to minus 3IZ minus 3I. Take W common, we get 2Z minus 3 minus Z equal to, here we are taking minus 3I common, Z plus 1. That implies W into 2Z minus Z is Z minus 3 is equal to minus 3I into Z plus 1. W is equal to minus 3I into Z plus 1 by z minus 3, or we can write like this, w is equal to 3i into z plus 1 by 3 minus z, right? So this is the required bilinear transformation. See another example. Find the bilinear transformation which maps the points infinity I 0 into the point 0 I infinity. Here also we have to find out the bilinear transformation. Points are given infinity I 0 and 0 I infinity. Let z1 is equal to infinity. First we have to note down the given points. z1 is infinity, z2 is I, z3 is equal to 0, and w1 is equal to 0, w2 is equal to I, w3 is equal to infinity. We have to find the bilinear transformation. Therefore, the required bilinear transformation, we have to write the formula first. The required bilinear transformation is required bilinear transformation w minus w1 into w2 minus w3 by w minus w3 into w2 minus w1 equal to z minus z1 z2 minus z3 by z minus z3 into z2 minus z1. Substitute the points in place of z and w. W minus, what is w1? w1 is 0. w2 is I minus w3 is infinity by w minus, what is w3? Again it is infinity. w2 I minus w1 is 0 is equal to z minus z1 is infinity, z2 is I minus, what is z3? z3 is 0 by z minus 0 into I minus z1 is infinity. W into I minus infinity by w minus infinity into I is equal to z minus infinity I by z into I minus infinity. In note, we already discussed the point. If one of the point is infinity, then in place of that we have to mention 1. I minus infinity w minus infinity, which is 1, and z minus infinity by I minus infinity value, which is equal to 1. Therefore, w by I is equal to I by z. W z is equal to I square or w is equal to I square is minus 1 by z, which is the required bilinear transformation for the given points infinity I0 into the points 0 I infinity. See another example. Find the fixed points of w is equal to 6z minus 9 by z. Here we have to find out the fixed points. W is given 6z minus 9 by z. Given W is equal to 6z minus 9 by z. So we have to find out the fixed points here. So to find the fixed point, we have to replace W with z. Now z is equal to 6z minus 9 by z, which implies z square minus 6z plus 9 is equal to 0. We get z minus 3 whole square, which is equal to 0. Z is equal to 3 comma 3. Hence, the fixed points are, so what are the fixed points that we get here? Fixed points are 3 comma 3. Two fixed points we get, that is 3 comma 3. So to find out the fixed point means we have to replace w with z. Then solving that equation, we get the fixed points. Next example. Find bilinear transformation whose fixed points are I comma minus I. Previously, we have to find out the fixed points, but now we have to find bilinear transformation. Fixed points are given I and minus I. Two fixed points are given alpha is equal to I. So the two fixed points we have to take, one is alpha and another one is beta. Beta is equal to minus I. If two fixed points are given, the bilinear transformation is formula W is equal to gamma z minus alpha beta by z minus alpha plus beta plus gamma. In place of alpha and beta, substitute minus I. For various values of gamma, W is equal to gamma z minus alpha is I, beta is minus I by z minus I minus I plus gamma, that equal to gamma z minus of minus, here we get plus I square by z plus gamma is equal to gamma z, I square is minus 1 by z plus gamma for different values of gamma or for various values of gamma. For various values of gamma. Therefore, W is equal to gamma z minus 1 by z plus gamma. Put gamma is 1, then W is equal to z minus 1 by z plus 1. Gamma is 2, W is equal to 2z minus 1 by z plus 2. So like this we get the values. We can take gamma is equal to 0 also. Gamma is 0, then W is minus 1 by z. So for different values of gamma, we get different values of z. So this is the procedure to find out the bilinear transformation whose fixed points are given. Here the fixed points are I and minus I, and the formula that we are using is W is equal to gamma z minus alpha beta by z minus alpha plus beta plus gamma. See another example. Under the transformation, W is equal to z minus I by 1 minus Iz. Find the image of mod W is equal to 1. So under the transformation is given W is equal to z minus I by 1 minus Iz. We have to find out the image of mod W is equal to 1. Given. So what is given here? Transformation is given, that is W is equal to Z minus I by 1 minus IZ. We have to find out the image of mod W is equal to 1. Consider mod W is equal to 1. In place of W, what we have to take? Z minus I by 1 minus IZ. Substitute in place of W. Z minus I by 1 minus IZ is equal to 1. That implies mod Z minus I is equal to mod 1 minus IZ, which implies Z is X plus Y. X plus IY. In place of Z, we have to take X plus IY minus I is equal to 1 minus I into X plus IY, which implies X plus, take I common here, we get Y minus 1 is equal to 1 minus IX, I into I is I square, minus I square Y. That implies X plus I into Y minus 1 is equal to mod 1 minus I X, I square is minus 1, minus of minus we get plus Y. That implies mod X plus I into Y minus 1 is root over X square plus Y minus 1 whole square is equal to, here we have to separate real and imaginary parts, then we get 1 minus Y, 1 plus Y minus Ix. So modulus of 1 plus Y minus Ix is root over 1 plus Y whole square plus X square. Then here square root is there and here square root is there. Then cancel these two, we get X square plus Y minus 1 whole square is equal to 1 plus Y whole square plus X square. Expand this, X square plus Y square plus 1 minus 2Y is equal to X square plus Y square plus 1 plus 2Y. X square cancel, Y square cancel. Here 1 is there and here also 1 is there. We get 4Y is equal to 0 or Y is equal to 0. So Y is equal to 0, which represents a real axis in Z plane. Y equal to 0, which represents 4Y is equal to 0, or we get Y is equal to 0. So finally we get the image of mod W is equal to 1. Under the transformation, W is equal to Z minus I by 1 minus IZ. Try the following problems. Find the bilinear transformation which maps the points 1 plus I, minus I, 2 minus I of the triangle T of the Z plane into the points 0, 1, I of the W plane. Here we have to find out the bilinear transformation. Points are given. Next, second question also, here we have to find out the bilinear transformation which maps the points minus 1, I, 1 in the Z plane into the points 0, I, infinity in the W plane. So try these two by using bilinear transformation formula. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.